to this chilly day, huh? Oh my gosh. It was 81 degrees when I got here. And, yeah, what are we down to now? I know it's not quite that warm anymore. It's 76 or 77 right now. So, yeah, we're making it through. You guys doing okay? Anybody faint at all? Okay. Maybe close during chapel because of all that standing. That was something. Okay. So, despite the heat, we are going to move forward today. Before we keep going, let's take a look at worksheet 2. Anything you'd like to talk about from this worksheet? Going once. Number 4. Okay. 4 and 8. Yeah, both of those sound good. So for number 4, we'll do the bar graphs first. So the car is at rest because original velocity is 0. The height is 0. So both of those things mean there's no kinetic energy and there's no potential energy. There's no springs here, so there's no spring potential energy either. So there's no original energy. Now at the top, you can see the car eventually gets a ways up that ramp. Velocity is equal to 0, and the height is greater than 0. So because it's not moving, there's no kinetic energy. But because it's above the 0 point, you would have some potential energy. In terms of the energy flow, because we didn't start with any energy, we'd have to do work on this system in order to get it to move anywhere. So energy flow would have to begin with work, and then as this person is pushing that car up the ramp, you've got kinetic energy because it's moving, and you've got potential energy because it's getting higher and higher above the 0 point. So that would be the second thing, and at the end you just have potential energy because once it stops moving, there's no kinetic. So that would be number 4. Questions on 4 there? Hopefully that makes sense. Number 8. So this elevator starts at the top. And at the top, it is above 0. You can see y original is greater than 0, so it's at a certain height. And the original velocity is greater than 0, so that means it's moving. So originally, you've got both kinetic energy and potential energy, because it's moving and it's off the ground. Now at the end, the height is 0 and the velocity is 0. So that means there's no kinetic energy because it's not moving, and there's no potential energy because it's on the ground now. So there is no energy at the end. In terms of the energy flow, you start with that kinetic and potential, and where does all that energy go? Heat, absolutely. If it did not go to heat, if it was conserved, it would have bounced right back up where it came from. Thankfully, elevators don't do that often. Anything else you'd like to talk about? Yeah.
For 8, would there be spring potential energy?
I mean, in the
string holding it up.
I probably wouldn't call that a spring potential energy. That is the reason you've got gravitational potential energy. For you to have spring potential energy, you need to have something that's like stretchy, something that will stretch or compress, like in number 7. You've got that bungee cord. You're going to have a good amount of spring potential energy there. Other questions? Yes? Okay, let's take a look at 7. So at the beginning, this guy's standing on top of the building. So he's got potential energy to start. At the end, that bungee cord is fully extended and he has no velocity. So he's definitely got spring potential energy because the bungee cord is kind of acting like a spring. And he's got a little bit of potential energy too because he's off the ground a little bit. If you can see, the bottom of his head isn't quite hitting the ground, so that's good anyway. In terms of energy flow, you start with potential energy, and then while he's falling, he's both off the ground and moving. So he'd have potential energy and kinetic energy. Eventually, that bungee cord is going to start to do its thing and kind of stretch. So then you would have kinetic energy, potential energy, and spring potential energy all at once. So you'd have all 3 of those. And then you'd eventually get to the point where the bungee cord is stretched all the way and he's not moving anymore. So then you just remove the kinetic energy. You'd just be left with spring potential and regular potential. So that's what number 7 would look like. Other questions? Okay, I'm going to come around and get these from you. And then get your notes out. All right, time for notes. Label your notes energy and work. Energy and work. Bless you. Energy and work. So, in this section, we've mostly talked about energy, and we've talked about how that energy can be gained or lost. Today, we're going to take that one step further and start assigning numbers to these things. And the way you get numbers with kinetic energy and potential energy and spring potential energy and things like work is by using equations. And those equations are on the formula sheet. If you look in the energy box on your formula sheet, you'll find all the equations that you need to know. And we're going to go through these one at a time today just to make sure there are no questions, and we'll be off to the races. First one you got to be aware of is kinetic energy. Go ahead and write this down. You can ignore this for now. We'll do the stuff on the little whiteboards first here. So kinetic energy is pretty straightforward. 1/2 mv squared tells you exactly what your kinetic energy is going to be equal to. So if you've got somebody who's 60 kilograms running at 8 meters per second, you're just going to do 1/2 times the mass of 60 times the velocity of 8 squared, and that tells you exactly what your kinetic energy is going to be equal to. Pretty straightforward. The only thing I want to mention is for the mass, it should always be in kilograms, and the speed should always be in meters per second. Furthermore, you see it's labeled with capital J there. Anybody know what that stands for? Joules, yep. So energy, the units on energy are joules, and that's what that capital J is going to mean. The next example that you can do is this one. This is how to find spring potential energy. This guy's pushing on a spring that's attached to a wall. So just a few little things about spring potential energy here. It's equal to 1/2 kx squared. This k is called the spring constant. It's a measurement of how strong the spring is. Remember when you were kids and you went to like playgrounds and stuff? You remember those things you could sit on that had the giant spring-looking things underneath them and you can wobble back and forth? Yeah, so that's a really strong spring. It would have a very large spring constant. You can see it's measured in newtons per meter. So it's simply a measurement of how many newtons of force it takes to stretch or compress that spring 1 meter. That's what that means. X is just the distance that it's stretched or compressed from the equilibrium point. So every spring is going to, have a natural length to it. And then however much you stretch it or compress it in, that's what this X value is going to be. So in this example, this guy is compressing it 0.2 meters inward. And to find that spring potential energy, 1/2 times the spring constant, which is 150, times the distance it's compressed, 0.2, squared, and that gives you a total of 3 joules of spring potential energy here. Yes? Yeah, it's a pretty strong force. Yep. Because if we think about it, let's see here. Newtons to pounds, I think 1 is 4.45. 1 pound, I think, is 4.45 newtons. Maybe it's the other way around. I'm going to find out real quick. Otherwise, it's going to bother me. Actually, I think it's on here. Oh, it's on our formula sheet. Yeah. So the number of pounds times 4 is equal to the number of newtons. So we'd have to divide this by roughly 5. So 150 divided by 5 would be 30. So this would be 30 pounds for every meter that it's compressed. So actually it's pretty weak. So this would be a pretty weak spring if it only takes 30 pounds of force to compress it that far. That's a really good question. I'm glad we figured that out. Okay. Also, from this, make sure that your distance is in meters. You do have to have that for your unit value. Last one we'll do is potential energy. Go ahead and put that in your notes. Bless you. So potential energy is pretty straightforward. It's mass times g times your height. So let's calculate this together. The mass is going to be 60. The G, well, for the G value, we need to make sure that we're aware of something here. In the motion section, we had to define this G value as negative 9.8 because gravity is pulling everything down at an accelerating rate. In the force section, we set G equal to positive 9.8 because the negative was taken into account when we would make the force equation. So the question becomes, what is this G, positive or negative 9.8? The thing with energy is that it's a scalar. So direction does not matter in energy. Therefore, this G value is going to be a positive. But yeah, for force or for motion, when we have to take direction into account for vectors, that's why we had to put negative values with those, whether it's through a force equation or the G value itself. And the height is 5, so when we calculate this all out, we'll get a potential energy equal to 2,940 joules. And that's what we get for the potential energy. Questions on that? Cool. Didn't think so. So, now that we know how to get these energy values, I want to show you something that I find pretty interesting. Let's say that this person, which has freakishly long arms, can no longer hang on to the ceiling that he's attached to there. And he lets go. If I wanted to figure out how fast he'd be traveling when he hits the ground, I could do that with some of the equations that we used in the projectile motion section. I'll just run through a quick calculation with you here. So, remember this equation? Yeah. Right? So, this is something I could use to find out how fast he'd be going when he hits the ground. Let's just run the calculation real quick here. Original velocity is going to be 0 because when he's lets go, he's not originally moving anywhere. So this is nothing. Then we've got 2 times acceleration, which is gravity, negative 9.8. And then the change in height is negative 5 because he's going down 5 meters. And because that would get us the velocity squared, I got to take the square root so that it gives us the actual velocity. And if we put this into our calculators, we'd end up with a value of 9.9 meters per second. And of course, because it is under a square root, the result can be positive or negative. So I would give this a negative value because it's going down. And that's how we could find how fast this guy's traveling when he reaches the floor 5 meters down. Which would be about 15 feet down. So he'll be going pretty fast there. So I want to show you how this can kind of apply to energy. Because physics is like one big circle. Everything is really connected. And you can solve this kind of a problem with energy just as good as you can solve it with projectile motion. Here's how. You guys ever heard of the conservation of energy? Yeah. So you can use that in order to figure out different numbers with this. So the conservation of energy basically just says, and here's where you can start writing again. Conservation of energy basically says original energy equals final energy. If from beginning to end you don't lose any energy to heat or radiation and nothing is gained through work, then you can use this equation to solve for all sorts of different things. So when this guy's hanging onto the ceiling, what is all of his energy? Potential, yeah. So originally, he's just got potential energy. When he hits the ground, or maybe right before he hits the ground, what is his energy then? Yeah, it's all kinetic. because all of that potential energy has transferred into the energy of him moving. So let's just see where this takes us. Potential energy is mgy. Kinetic is 1/2 mv squared. Well, look at that. There's a velocity within kinetic energy. So let's solve for that v, and we'll just see what happens. You could put the numbers in right here if you want. What I usually do is isolate the letter, because oftentimes you can cancel stuff out, and that's what happens here. So if I want to get this v by itself, I would multiply both sides by 2 then. So this would be 2gy equals v squared. And of course, if I want to get rid of that square, I erase it. But if I do that, I got to square root the other side. So if I plug those numbers in, and again, g is positive here because we're dealing with energy. Bless you. Bless you again. And then our height is 5 meters. That's our starting height. So if we take the square root of this, that's going to get us our velocity. Guess what it comes out to be? 9.9. And again, when you plug this into your calculator, you'll get a positive value. But because you're going down, that velocity you can just say is negative. Because if you're under the square root, it can be positive or negative. So yeah, this is just awesome. You can get the exact same answer using projectile motion as energy. Neither way is better or worse than the other. And this is what makes physics so neat when you start getting further into the class like we are right now. Once you see a problem like this, if you hated those equations in the projectile motion chapter, you can just say, you know what? I like just starting with original energy equals final energy. You can totally do that and get the exact same answer. And a lot of the questions you'll see on the homework are questions that you could solve using force or projectile motion. So yeah, it's just another way of looking at the world and describing exactly what we see. Questions on this? Let's do another example. Let's use the example that we used for kinetic energy here. I'm just going to erase something. Here's our example. Put this down. Now instead of just running, this guy's running towards his beloved childhood spring. He's an interesting fella. So my question on this one would be, when he runs into that spring, that weak little spring that we found, it only takes 30 pounds to compress it 1 meter. The question is then, how far is that spring going to compress? 60 kilograms is a pretty average weight for a high school student. So it should be interesting to see how far one of you guys would end up compressing this spring here. The velocity, we'll say, is equal to 8. Let's say 8 meters per second for the velocity. And that's about as fast as a standard person can run. About 16 miles an hour or so. So let's see what happens. At the beginning, all of the energy is kinetic because he's running. At the end, all of the energy would be spring potential because eventually he's going to come to rest after he compresses that spring as far as it's going to go. So let's see if we can find out exactly how far that spring's going to compress. One halves go away. If I want to solve for the distance x, I'm going to isolate it, and I start that process by dividing both sides by k. And of course, we've got that square there. Those squares seem to be everywhere with energy. So in order to get rid of that square, we got to take the square root. And once you run that calculation, you'll get a distance that is very large. As you could probably imagine, running headlong really fast into this weak little spring will get you a distance of 5 point something, 0.06. In other words, you're going to be compressing this spring roughly 15 feet or so. That's a big spring. Questions on this? Okay. I've got one more thing that we need to talk about. You guys ready to do some work? Wink, wink. So when we talk about work, you can find it defined on your formula sheet in a couple of different ways. Work's equal to two things. Work is equal to change in energy, and it's also equal to force times distance. You might want to label this section in your notes, work. And of course, because energy can be kinetic or potential, you can define it in both ways. So, change in energy is pretty easy to see. If you can somehow measure your kinetic energy at the beginning and, whatever energy is left at the end, if there's some difference between those two numbers, that means work has somehow been done on that system. Either work was, added energy into the system, or maybe friction did some work and took energy out of it. But yeah. That's one way to measure work. The other way is force times distance. So let's say I have my little binder here. We'll say that it weighs 1 kilogram. And I move it, we'll say I move it 1 meter across the table, and I'm exerting a force of 5 newtons to move it. So the force would be 5 newtons as I move it across, and because it moves 1 meter, it would just be 5 times 1, and that would give us a work of 5. What do you suppose the units on work are? The hint is kind of up here.
Triangle.
Triangle. Joules, yes, because if work is just change in energy, then it's just going to be the same units as energy, which are joules. So that would be the easy way to do work. Now I got to show you kind of the more in-depth way. You'll notice if you look at your formula sheet that the way work is described is a little bit more specific than what I have on the board. On your sheet, it says F with a little x next to it times distance, and F with a little y next to it times y. I'll show you exactly why those are there. So what we've got here is we've got a box that's going to move from left to right on this table a total of 9 meters. The force being applied is 20 newtons, and that force is applied not horizontally, but at a 40-degree angle. So if it's applied at a 40-degree angle, it's going to give us something that's a little bit more complicated to deal with. When we say force times distance here, this force is specifically the force that's acting in the direction that the object is moving. So because this object is moving horizontally, 20 newtons is not going to go here. What's going to go here is how much of that 20 newtons is actually acting horizontally. So, I know you guys are sick and tired of sine and cosine by now. They're going to rear their ugly heads one more time. So, if this is 20 newtons here, we got to basically solve for what this side of that triangle would be, the adjacent side, because this is going to tell us exactly how much force is going horizontal. And whatever that horizontal force is, that's what's going to go here for that Fx. So you can see with a blue arrow there. This would be your force in the x direction. So, just kind of as a cheating way to do this, because we've done it so much that we're all sick of it, if you're looking for a horizontal force, you'll always be using the cosine function. So another way to write this in the x direction is just going to be your force times your distance times the cosine of whatever the angle is. So it's just going to be 20 times the distance it moves, 9 times the cosine of the angle. So just do that when you do it. If you're moving vertically somehow, which is more rare, it's the same idea, except sine. So hopefully that's a little bit less painful than it could have been. The little x just signifies that this force is the force that's actually acting exactly in the x direction, horizontally. And that's what we're doing up here. Like, this is 20 newtons coming down at a 40-degree angle. So, to find out what this side of the triangle is, I'd have to go, cosine of 40 degrees is equal to adjacent, which is Fx, over hypotenuse, which is 20. Therefore, Fx is 20 times the cosine of 40 degrees, which is where that comes from. I just left the 9 in here because it looks a little bit nicer that way, but whatever. Yeah, if you're doing it this way, you could say 20 times the cosine of 40 multiplied by the distance of 9 meters. Questions on this?
No.
Cool. That is. Now I'm going to hand out the homework, and I think we'll do one of these together.
Okay.
Again, you will have tomorrow to work on this in class. After
Who wants to sit there?
I'll leave it at that. You're welcome.
Here,
You got it.
This is it, 22nd.
Today is the 24th.
Thanks, Jeff.
You're welcome. Let's go through number 2 together. So number 2, well, number 1 and number 3 you're doing basically like the examples we did in class, but number 2 has a little wrinkle in here. it says, assuming 10% of the system's energy is lost to heat via friction, what is the cart's final velocity? So we're going to set this up pretty much the same way we'd set up any other conservation of energy problem. And at the beginning, we've got our original energy. At the end, we've got our final energy. At the beginning, this little cart is on the top of that hill, and it's not moving. So all of its original energy is potential. Eventually, it reaches the bottom of that hill, and it starts, and it moves. So when it's at the bottom of the hill, there's no more potential. All of the energy is now kinetic. Now it says 10% of the system's energy is lost to heat. So how much of the energy is left? 90%. So the easiest way to approach these problems then is to just multiply your original energy by 90%. In other words, 0.9. Right. Yeah, you could do that too. So yeah, because this would mean that now you've got 90% of your original energy that's going to transfer into the kinetic. So the equation would just go like this. And let's see here. Our original height is going to be equal to 5 meters. The mass is equal to 20. And of course, the velocity is what we're looking for. And so you could go ahead and solve it this way. You could solve it the same way that I went through the ones earlier, where we would cancel out the masses and just solve for the letter first, whatever you feel like. In the end, number 2, you should end up with 9.39 if you want to check your answer with that as you go through. And the very last thing that I'll mention here is friction. Friction also rears its ugly head in problem number 5, letter C. You must remember that force of friction is equal to the coefficient of friction times normal force. Of course, this is also on your formula sheet. I just wanted to make you aware of it. Any last questions? Alrighty. You'll have tomorrow to work on this.
What's the answer to
Number 2, the answer was 9.39 meters per second. That's what you should get.